Welcome, Mark. How's it going?
It's going great. It's a Friday afternoon, so just excited to talk about this with you guys today.
Yeah, tell us about who you are, Mark, before
Yeah,
we
so
get
my name
started.
is Mark Klein, as you know, and I am the product manager here at AWS for our new service called AWS Payment Cryptography.
All right. How excited about this are you, Jeff?
Well, I kind of set the stage earlier.
You did.
I think cryptography is in itself kind of complex, and I think the stakes are high because the data that is most important to be guarded is very valuable data, especially what I mentioned, PCI stuff, payment card industry stuff. So I know a lot of enterprises, and it doesn't even have to be an enterprise, but anyone handling credit card data needs to be part of the PCI industry and needs to safeguard your credit card data, my credit card data. And there's a lot of resources that go into that. And it sounds like this new AWS payment cryptography can just simply make that easier for customers. And that's what I'm excited to talk to Mark about.
Yeah. Mark, so cryptography, right? I think almost everybody watching, if you don't know already, cryptography has lots of applications. One of the primary ones is encryption, right? And encrypting data is securing data. It's obscure. It's completely making the data unretrievable, except if you have these cryptographic keys. Uh, it powers a lot of things. Powers the HTTPS that is coming across to you right now as you're watching. But Mark, what's special about payment cryptography? That's what I want to get to before we talk about the product itself.
Yeah, absolutely. So cryptography is used extensively in payments, especially card payments, because Jeff talked about it earlier. You're trying to secure data in some way or another, fundamentally, usually with cryptography. And what's more important to secure than money? So fundamentally, it's used to ensure that people are able to authenticate the actual transactions. People aren't able to inject, for instance, fraudulent transactions into the ecosystem. And then also, when you're going to make a purchase, that it can be verified that it's really you, that you've typed in the right PIN code, that it's actually your card, and somebody hasn't made a copy of your card, as an example, cloning, which has been in the news a lot. So cryptography is used quite extensively to secure the data going between all the different entities, the merchants, the networks, back to your bank, and then also to make sure that it's really you who is making that purchase in the first place.
You were even mentioning when we were talking about the segment in the prep that pieces of the credit card, like the actual sum of the numbers, the CVV2, I believe is what you said,
Yep.
is an actual cryptographic value itself.
That's right. That's right. So a lot of people think that value is just a random 3-digit number or something like that. That's actually a cryptographic value, a secured value that's unique to that particular card, and only your bank can determine whether, when you type it in, whether that's the right value or not. So they're all over the place. They're hidden in the mag stripe if you still have an older card. They're in the chip as well on newer cards. Also, if you're using Apple Pay or something like that, there's cryptograms as well. So even from the oldest technology of mag stripes to the newest technology like Apple Pay or Google Pay, it's there in almost every single card transaction.
Now, Mark, traditionally too. Look, fundamentally, right? Like when you're a developer, or you're somebody setting up one of these systems, right? To interact with cryptography, you usually have some kind of library that is an implementation of some kind of encryption algorithm like AES or something, right? And then you just start using values and encrypting values with it. But with payment cryptography, there's actually some like hardware involved oftentimes as well. Do you want to tell us a little bit about the actual like HSMs that are involved in payment?
Yeah, absolutely. So there's two parts of it why it's different than just regular cryptography or encrypting or decrypting data. The first one is around the security of that data. So as you kind of mentioned, in order to maintain that security and to maintain PCI compliance, which helps enforce some of these rules across the industry, many of these cryptographic operations have to happen on secure hardware called a payment HSM. And HSM is a hardware security module. So these are specialized hardware that's used to secure the cryptography so that nobody, going back to the conversation, I think, about Eve, so that nobody can be listening in, right? Because these hardware modules, essentially everything's happening very securely within them. There's no ability to, for instance, read the memory on another application within an application or anything like that. So it's impossible to see anything that's happening in the middle, or to see the keys in the clear, as an example.
Yeah, Mark, and I'd imagine that managing your own HSM is pretty complex and probably pretty expensive.
Absolutely, because this is a critical part in transaction processing, and if you can't run it, then your transactions are going to start failing. So it's obviously a high stakes part of running a business that takes payments or processes payments, which is almost everybody in a way. So typically you have to have a fleet of HSMs. You need to have another fleet in a second location for high availability. You need to think about disaster recovery. You need to think about, do I have enough volume to account for Black Friday or Amazon Prime Day, as an example. So there's a lot that goes into it. Also maintaining that compliance that you talked about before, Jeff.
Well, yeah, I was about to say physical security as well of those HSMs.
Yeah, physical security, logical security. You need to keep up on all the latest patches as well. Obviously, just with anything else, there are occasional flaws that are found and issues. So you need to keep up on all of that as well. Otherwise, you will obviously put things at risk, but then also you may fall afoul of PCI compliance.
Yeah, and for all of our viewers who might work in data centers, I'm talking there are certain racks that might have a video camera watching the rack at all times. The subflooring underneath those racks have to be special so no one can crawl under the raised floor environment and tap into network cables. There's a lot that goes into guarding the physical security of these HSMs.
They thought about me. That's exactly what I would have done. Robert, not to totally derail the conversation, but I do love this. Robert, tables. Number one, I'm much too young to remember this.
I remember.
I have no idea what this is. I'm just super young, so I don't know what he's talking about here. Yeah. But they would bring out the big machine, and somehow I know the motion.
Yeah, that's weird. I was gonna say, you know exactly what it sounded like. Yeah.
Yeah, I'm too young to know. So, but I somehow know the motion. I probably saw it in a movie. Anyway. Do you remember these?
Knuckle busters is what they were called.
I never knew that. That's interesting.
It doesn't work as well. That's why the numbers are raised. Fun fact. That's why the numbers are raised on some cards, is so that would work. And you kind of notice on the newer fancier cards, they don't raise the numbers anymore. So obviously you wouldn't be able to take an imprint like that anymore.
I love learning simple things like that make perfect sense, but you would never kind of piece it together unless you knew. Because some of the newer cards, I'm like, oh, this is nice. No raise. Okay. Yeah, it's awesome.
Now, Mark, I'm also going to save a question for the end too. You mentioned Prime Day. I'm very curious if you bought anything and what you bought on Prime Day, if you're willing to share. But let's save that for the end. That's a reason to keep watching. Mark, can you walk us through like what a transaction end to end looks like and who's involved? I know you've got a demo for us, and I think you got a nice visual that lays this out. Do you want to bring that up at this point?
Yeah, that'd be great. Why don't we share my screen, if that's all right? So for those that don't know or aren't as familiar with it, for card payments, which is really what we're talking about today, is what's called the four-party model typically. And the four parties that are in that model are the cardholder, so the person actually trying to make a purchase, and I'm kind of working around the shoehorn here. The cardholder, the merchant that you're trying to buy something from, the acquirer or the acquiring bank, so that's essentially the bank of the merchant. And then the last one is the issuing bank, which is essentially the bank of the cardholder. So these are the four entities that are involved in most transactions. You obviously have kind of a fifth entity as well, which is the card networks, the entity that most people actually think about normally, which is Visa and MasterCard, Discover, American Express, and so on. And they actually are the glue that helps bring this all together. But just for simplifying the diagram a little bit, we're not going to talk about them today.
My Lambda detection for recursion radar is firing right now because I could see myself getting in a recursive loop of purchasing something over and over and over again, following your pattern here.
Oh man. Well, I mean, that's where you end up with a big bill at the end of the month.
Yeah,
right?
That's my own.
Keep on doing that, especially the one-click button on Amazon, right? It makes this very easy.
It's my own weakness. That has nothing to do with Lambda, actually.
There you go. There you go. So we're gonna walk through a demo today, kind of just showing where payment cryptography fits into the flow. We kind of talked about the CVV2, we talked about the chip cards and things like that. It's kind of hiding there in plain sight. Going back to that earlier pun about the bar, there's cryptography everywhere, and as a consumer, obviously the intention is that you don't need to see that, but it's what's keeping your transaction secure ultimately. So it's important. It's behind the scenes. But it's what's keeping everything safe and secure and letting you trust that you can continue to use payments. So this example, we're going to start out sort of at the very beginning. So we're going to start out. You're the card holder, and you got a new card in the mail. Yeah, you could be the card holder. There you go.
My wallet. This is filled with Jeff's credit cards. Is that okay?
No, I think it's just filled with receipts, and he can barely close it.
Yeah, fake badges and whatnot.
Like George on Seinfeld. Is that okay? I got the reference. All right.
You're old enough for that one.
Yeah. Oh no, I saw it in a rerun. Wait,
Okay.
well, that's a rerun though. I saw it in streaming. Sorry.
There you go. There you go. So the first thing we're going to do in this case is the card holder is going to set their PIN, and for the purpose of this demo, we're going to I set up a little toy ATM, little demo application. So I got my opportunity to do a little coding.
I like it.
To make this demo.
That's what we call a callback.
What language? What language of choice?
Oh, Python.
Python. Okay.
Python's the language to go to for quick things, I think.
Incredibly popular, especially here at AWS. Everybody I talk to, I'm a C# guy by tradition, JavaScript guy in practice a lot of the time. Done some Python, but man, that is popular. It is popular around here.
Yeah, it's great for quickly doing things, I think.
So you're using the Python SDK, Mark, from AWS?
I sure do. Yeah.
Moto 3?
Yep, Auto 3. That's right.
Nice.
So we're going to have a little test ATM. And what we're going to do is we're going to set our pins. So I think you're familiar with that. A lot of times if you want to change your pin or something like that,
Sure,
you might go to an ATM to do it. Now, there's other ways to do it. You can do it in an app and things like that these days. But for the demo, we'll show it at an ATM. It's going to make a call back to so one of the big things about PIN data, especially, is you don't want that data in the clear flying through various different networks and middlemen and things like that. So typically, PINs are encrypted as soon as you type them in. So that way, there is very minimal chance, almost zero chance, of that data being compromised. Because if somebody has your PIN, then they can go and make other purchases on your behalf. Another Seinfeld reference there would be that the PIN is Bosco.
Bosco,
yeah.
Bosco.
There you go. There you go. So that's gonna. So what's gonna happen is the ATM is gonna immediately encrypt that data and send it down to the issuing bank that you can see here in this diagram. The issuing bank is actually going to perform. So first of all, the ATM performed a cryptographic operation. Then when the bank gets it back, they are going to essentially within the secure environment, which in this case is AWS Payment Cryptography, is going to read that data. And then actually, instead of storing the PIN, which even with cryptography, there's always the risk that somebody may figure out a way to read it or something like that, or do some sort of replay or comparison attack or something like that. So instead of actually storing that data, the bank is going to generate what's called a PIN verification value. And that allows them to safely store something that they can compare later on without actually storing the underlying PIN itself. So a lot of the times, you may go to your bank and say, "Can you just tell me the PIN? I don't know it." And they may say, "No, the best I can do for you is help you reset it." And this is one of the reasons why. So that literally, that way you don't have to worry about like any bad actors at the bank or something like that, somehow being able to read your PIN number. Literally, you were probably the only person who knows it.
It's like a password, right? You should never store plain text password.
Exactly.
Database.
Yeah. Yeah. It's pretty much like a hash, similar to how you store passwords, but very specialized to payments. So going back to why do you need these devices and things like that? These algorithms are quite often very specific to payments, and they vary in concept. Obviously, it's cryptographic techniques and things like that. Right. So those concepts don't vary, but the actual implementation and how they're done and the number of iterations through things and things like that are typically specific to payments.
Yeah, Mark, can I trouble you real quick? Just
Yeah.
for anybody who's watching who maybe is new to cryptography, what's the difference between encryption and hashing? Right, like that's something that I think people who haven't heard those terms before may not know.
Yeah, absolutely. So fundamentally, on a very simple level, encryption is a two-way operation. So anything that could be encrypted, if you have the matching key, you should be able to decrypt it, so you can get back to the original values. Hashing is one-way algorithms. So what that means is that if you have the output, you can never go back to the input again. And the benefit of that is that you don't need to be as careful with the data. And what happens is, in order to verify, you typically you'll run the hash again. And what you do is you just compare the results and you make sure, as an example, if I hashed a document to make sure that it wasn't edited between when I sent it to you, what I'll do is when I receive the document, I'll run the hash again, and I can determine whether or not somebody in the middle added the word "not" into a sentence or something like that.
Yeah, hashes should always, so if it's the same data, it should always produce the same value on the right hand side. And it's like you're saying, used a lot for data validation, right? So you download a file from the internet, oftentimes the publisher of that file will have a hash that you can validate that the file is the file that you were trying to download. Super interesting stuff. It's where salts come into play too when you're doing hashing too, where you can add in values to
and you have cryptographic hashes and non-cryptographic hashes as well. We could do a whole session just about that for sure.
I know. I love this stuff. Anyway, sorry.
All right, so we're now at the point where we've we're now done with step one. So we actually got on to step two. So the issuing banks stored that data for later on, and they're using that PIN verification value. Now we're going to go and actually make a purchase. So we got a little toy store that we're making a purchase there. I got kids, so most of the things I'm buying are toys or Pokemon cards or something like that. So we're going to make a purchase. This purchase requires a PIN code. I'm probably using like a debit card or something like that if I'm in the United States. So I'll type in my PIN code. Similar to what we saw for the ATM, the terminals themselves in a store are also secure devices. They will actually immediately encrypt that data using a key. This is actually a one-time key. It's a standard called DUCPUT, which is derived unique key per transaction. So we'll encrypt that PIN right away so that nobody at the store, nobody on their network, even if Eve is sniffing on the network at the store, she won't be able to read that data. They forward that PIN. I'm looking at step number 3 now. They forward that data to their acquiring bank. So again, this is the merchant's bank. That merchant bank also can't read the data. You don't want this other entity, who's probably not even somebody that you know, actually being able to read your PIN, because then they could make purchases on your behalf. But what they do need to do is they need to what's called translate or re-encrypt the PIN. So what this means is they have a key that they share between the merchant or the terminal at the merchant and themselves, but that's not the same key that they're sharing between themselves and the issuing bank. This is a concept around sort of segregation and separation. So rather than having one master key that everyone in the entire ecosystem is sharing, as you can imagine, eventually it would probably get lost if everybody had the same key. So you use different keys between different entities and different parties. So what they're going to do on step number 5 is they're going to what's called translate or re-encrypt the PIN. This happens again within that hardware. So that way, as one operation. So the acquiring bank, they never see the PIN. It gets essentially decrypted and re-encrypted all within the HSM, all within a single command. And that way, nobody is actually ever seeing the PIN data itself. And then lastly, we get to step number 6. The issuing bank, they get that incoming value coming in from the acquiring bank, and then they have that value that they stored at the very beginning. They're going to compare those two values, and again, going back to the comment about hashing before AM, essentially that's what's going to happen is inside of AWS Payment Cryptography, it is going to decrypt that data that they just got from the acquiring bank, and then it's going to regenerate that PIN verification value or that hash and determine whether or not they match or not.
Okay.
So essentially they don't know what the right PIN is, but they are able to regenerate that hash value essentially and determine whether or not it's the right one or not. And then you get approved or declined based on that. We're assuming you're good for the money, AM. So
Like I
you're
said,
looking at the passcode.
full of Jeff's cards. So he's loaded. Just kidding. I don't know anything about Jeff's financial situation, nor should I broadcast that out on the live stream. Apologies, Jeff.
Okay, Mark. So can we see this in action?
Yeah, let's do it. So you can see here, I got 4 screens. Going back to the 4-party model. Top left, I got the ATM. Hopefully you'll enjoy my my ASCII art.
Now,
I love it.
Did you create this? Or
some of them, yeah. There's also websites that will do it for you, which is pretty neat.
The toys one, I'm not gonna lie to you, Mark. The toys one is a little disturbing. Like, I think it's the why. The spacing and things. I look at it and I see toy, and I'm like, is this? Yeah.
You're not gonna buy toys. You don't trust buying toys from my store.
You're getting called out in the chat too for being an avant-garde artist.
There you go. I'll be signing later on.
This is bringing up memories of dialing into local BBSs on our 1200 baud modems that would play door games with these type of graphics. But I do remember ATMs with this same type of art as well. So
yeah, there you go.
I am that old.
Yeah.
I'll let you know.
The worst was when somebody would pick up the phone, though.
Yeah. But all of our viewers, I'll let you in a little secret. I think me and AM are about the same age.
What?
But anyway, go ahead. Continue.
All right.
Wait, you're 22 also, Jeff?
Yeah.
Okay.
All right, Mark. Sorry about that.
You can see here. So just real quick. So on the ATM screen, as I mentioned, it's going to be doing some cryptography itself. Within its hardware, so that's not using this particular service. And you can see just for obviously this is not very secure, but for the purpose of discussion, printed out the key that it's using. It's using an algorithm called triple des, which is it's a little bit of an older algorithm, but it's still used predominantly in payments. You can see here, I'm creating the most difficult passcode ever to know, 1, 2, 3, 4.
How did you know my PIN already, Mark?
There you go.
I'm kind of concerned.
I mean, that sounds like the type of pin someone would have on their luggage.
Or just every
Thank
pin that I've got.
Yeah, there you go. So you can see here, just talking about it really quickly, you can see it encrypted the pin. So I had this value that's non-readable now. So this could be passed a little bit more easily across insecure networks as 95180. And then you can see here, over here on the bottom right here, this is my bank server. So it's calling to the bank. And the bank is, as I mentioned, the bank is reading this data and then generating that PIN verification value. And it's doing that using AWS Payment Cryptography. So you can see here, I'm not going to go into all the parameters that are involved, but you can see here that I am using bot03 to answer your question, AM. And I'm calling the generate PIN data API. I'm specifying a bunch of different parameters, like what kind of PIN block it is. PIN block is the way that the PIN is stored within that encrypted data. It's like a certain format.
Oh yeah, I see ISO. So I imagine this is a standardized format, right?
Yeah, it's a standardized format. Yeah, exactly. There's a lot of ISO, a lot of ANSI standards used within payments. And then I'm also passing in this 9518 value, which, as you can see, that was the value that came in from the ATM. So that's the input. And then the output is a little bit harder to read. But the main thing that it's generating, as I mentioned, is the PIN verification value. In this case, you can see it's 3062. And that's not the PIN code I typed in. Hopefully that's relatively obvious. It is a 4-digit number. It's not the number that I typed in, though. So they'll store that. And again, it's a one-way thing, essentially, where even if somebody at the bank were to gain access to that, it's not actually your PIN code itself. So that's a little bit about how that works. Now I'm going to move over to my toy store. Hopefully you're willing to buy from my toy store, AM.
I feel like you're trying to lure me into your toy store a little bit. I don't
That
know.
sounds a little disturbing.
It does. It does. But you know what? I'm in. Let's buy some toys.
All right, let's buy something. So it's going to be $54.99. And you can see here, this is on the terminals. They use another standard called duckput. And that's, as I mentioned before, that's a derived unique key per transaction. So this is another layer of security rather than having sort of a static key, which over time, given enough situations, static keys could be compromised, perhaps, encryption keys in various different ways. This mechanism actually changes that key for every single transaction so that your transaction is even more secure.
Oh, wow.
So you can see here we started out, and here we're using AES, which is another encryption algorithm. So we're not using triple DES. The industry is kind of in a transition period where some places it's triple DES, some places it's AES. It's a great example of using the service. You can kind of switch back and forth between them in different points, and you'll see that here. What you'll see is we created a one-time key, this one that's A81, and that's the one that's going to be used for this transaction. It won't be used again. The next transaction will have a different key. So you essentially can't predict what the key is going to be.
Now, Mark, I hate you're on such a great roll, but I always like to bring along the audience when we can and teach them a little bit while we're here. So AES, triple DES, these things are often commonly referred to as symmetric, right, encryption algorithms versus asymmetric. Can you tell us, and I'm happy to take it too, I don't want to put all the onus on you, but why is symmetric? Why are we using, number one, what is a symmetric algorithm? And number two, why would that be beneficial to use during a payment transaction versus using asymmetric keys?
Yeah, absolutely. So symmetric keys are where the secret that's shared to encrypt and decrypt are the same. So if I have, essentially, it's almost like a passcode. If I have the passcode, and you can see these are long passcodes, technically binary data. But if I have that passcode, I can both encrypt and decrypt from a technical perspective. The reason why they're very popular is they're incredibly fast and they're incredibly efficient. So they're able to be done very easily, even on lesser hardware, like what you might have in an ATM or what you might have at those little terminals and things like that. Also, if you just think about payments, there are billions of payments going on all the time.
Yeah.
So from a pure scale perspective, symmetric encryption is very, very efficient. Also, somewhat outside of payment cryptography, but if you have larger payloads as well, like say a whole document or something like that, that efficiency really comes into play as you're encrypting more and more data. The other encryption mechanism is called asymmetric encryption. Typically RSA or ECC are the two most popular ones. RSA, very popular, going back to your TLS conversation earlier. And the way that those work is the two parties, the sending party, the encrypting party, and the receiving party or the decrypting party have two different parts of the key. So what happens is the person that's encrypting, they have what's called a public key that allows you to encrypt. And then the other party, the decrypting party, the receiving party, they have what's called the private key. So only the entity that has the private key can decrypt the data. It's a great technique. The public key is, as it says, the idea is that you could probably just put it on the internet or write it on the side of a wall or something like that. It's not intended to be a secret in the same way that symmetric keys are. And then it's that private key that's secure and a secret, and you don't give that to anybody else. There's usually only one entity or one system that has that key. It's super secured. The negative of that is that those algorithms are not nearly as efficient. They require a lot more computational power. So they're either not used, or quite frequently they're actually used just to encrypt a small piece of data, such as a symmetric key.
Yeah.
So what you'll actually see in practice a lot of the times is asymmetric keys are used to protect a one-time symmetric key.
Yeah.
And then the actual encryption itself is done using a symmetric key.
Yeah, that's what TLS does. I promise, Mark, I won't ask you to explain Diffie-Hellman. We don't have time. But yes, that's thank you very much for
Yeah.
taking the time to do that. I think this is really complex stuff, right? But it's really not once you start to learn these terms and you start to understand the applications of them. In the words of Sonic the Hedgehog, got to go fast, right? That's why you're going to use a symmetric key in a payment transaction. Got to go fast.
Right. That's right. All right, so let's get to it. So I'm going to enter my PIN. I'm trying to make my purchase. The person at the store got very impatient during that conversation.
Absolutely.
There was a whole line queuing up behind me.
You would hate to see me at Target, man.
There you go. So we're just going to go back to the store real quick. So you can see here, it again encrypted my PIN. You can see that it's a different value than earlier, right? Before it was 951. This is F70. First of all, it was a different key. This was a key for the merchant. Second of all, it's longer. You notice that the string is longer. That's because it's AES. It's a longer encryption algorithm. So you can see it's totally different. You can see that I forwarded this information to the acquiring bank, which is, again, the merchant's bank. That's this window up here in the top right. I got to scroll up a little bit. But you can see, as I kind of mentioned before, you can see received a request. Here's the information. And again, as I mentioned earlier with the diagram, the acquirer is going to forward that to the issuer, but you don't want to have the same key used or the same master password used everywhere, right? So this is where, again, where the AWS Payment Cryptography comes into play. We're going to call the service, and what we're going to do is we're going to translate or re-encrypt the PIN from here. You can see we're calling it the BDK alias. So that's essentially the key that came from the terminal, and we're going to translate it. The outgoing key is the issuer PIN encryption key alias. So we're going to translate it to the format that the issuer can read. We're also, if you remember, we're also sort of translating here between AES and triple DES. So this is a good way that you can sort of migrate between that transitional period within the industry. And then what we're going to get at the end out of this is we're going to get another PIN block or another version of the PIN. And this one is E33. So it's not any of the ones that we saw before, because this is a key that is shared between the acquirer and the issuer in this case. So we have a lot of different keys involved, right? That's one of the things about symmetric keys is typically they're either shared between one entity, like a bank itself, or a bank and one other entity, like a merchant or a terminal, and so on. So there's a lot of different keys, frequently thousands of keys being involved to keep everything secure.
Mark, when you talk about this translation, is that just like encoding the data in a special way?
So it's decrypting and then decrypting and then encrypting it immediately with a different key. So imagine you have a secret. I'm going to decrypt it and then I'm going to write it with a different code.
Okay.
But what's really important here is that in terms of the PIN, you don't want anyone to see the PIN. So you don't want to, for instance, do this within your code, within your Java code or Python or C#, because that means that within your application, within the memory, for instance, that for a brief second, the PIN is actually clear, right?
Yeah.
So, your application could be written wrong. Somebody could attack the memory and so on. And that's why the PCI compliance, as Jeff was talking about earlier, actually mandates that stuff like this happens within a secure device.
All it takes is one log statement, right? One print statement.
That's right. Log.info.
That's right.
Yeah, absolutely. So you can see here now the acquirer is passing this new encrypted PIN back to the bank so that the bank gets a final call, like, was this the right PIN or not? And then you can see, just going back to our bank window here, we got a call in to verify the PIN data. So was the PIN right or not? Again, we're using AWS Payment Cryptography, again, Botto 3. In this case, we're using API called verify PIN data. We're passing in the key, the PIN here. And we're saying, and then we're passing in, remember this 3062, that was that PIN verification value we had gotten on step 2. We're passing that in as well. And it's going to compare. So what it's going to do within the security of the service, it's going to decrypt the PIN that's encoded within this E33. It's going to decode that, generate the PIN verification value again, like a hash, as we were talking about earlier. And then it's going to say, does it equal the two values? And what you can see here is the answer was yes. And it responded back approved. And then you can see it starts working its way backwards. So now the acquirer got a approval as well from the issuing bank. And then that finally went back to the terminal. And then the terminal says, your transaction's approved. And
That's awesome.
That's how you get to walk out of the store without
Wow.
Yeah, it's interesting to think that all happens in what, like
5 to 7 seconds.
Yeah, well, it seems quicker, but you were telling us earlier that that's it has to be 5 to 7 seconds. All of that encryption has to, I mean, before you get an accept.
Yep, exactly. And all that encryption is a very small part of the 5 seconds. They also got to check, for instance, do you have money?
Right.
That's a good example, right? So there's all sorts of things happening. And also think about what if your bank is in the United States and you're buying something in the UK or something like that. You also have the time itself that those bits need to fly around the world.
You got network latency throughout this entire process for sure.
Yeah, absolutely.
What I love, Mark, and please tell me if I'm right here, these things like the translation where it needs to be decrypted and then re-encrypted, you don't have to do that. Like as a dev, you just call the SDK and that is happening. Is that
that's absolutely correct.
I love it. That's that right there. If nothing else, I mean, the whole thing is incredible, but that right there for me personally, that's incredible because like we were talking, it's very easy to mess this stuff up. Very easy to write one wrong line of code that costs your compliance, right?
Yeah.
Like
the stakes are high. Not only your compliance, but customers' money, basically.
Right. For sure. That's awesome, Mark. And then the verification also happens through the SDK as well, right? Like
that's correct.
And the service.
Yeah.
Wow.
Yeah. So Mark, who would it be the devs, or who would be the customers that could benefit right away from this new service?
Sure. So I think as we saw in the diagram, in terms of companies, really anyone that's involved in card payment processing, people like acquirers, merchant gateways, payment gateways. So these are a lot of additional entities. I showed 4 parties. There's actually a lot more quite often.
Because
issuer processors. And then at those organizations, a lot of the times, because this is security related, it's frequently within a security engineering org.
Gotcha.
Sometimes it'll be somewhere else, but frequently it's there. And the interesting thing about this is that, I think as AM was getting to, it's quite complicated, right? And a lot of the times people, especially in security, this is interesting. It's cryptography. Cryptography is cryptography, I suppose. But there's lots of different avenues, right? And there's a lot in here. There's 30, 40 years of history. We were talking about the raise cards before. So it's hard, it's hard for a small number of people within a security engineering team to really understand this and keep those and traditionally keep that physical hardware working. And what we're really trying to do here is make it easier and help lessen that burden for those people in the organization.
Well, speaking of lessening that burden, and we talked about PCI, payment card industry. If you remember, you have to go through an audit, a yearly audit, and you have to supply evidence, and you have to kind of state your case to the auditor. And when we have those conversations, we always talk about inheriting, and especially my work with the DoD, we talk about inheriting controls. So how does this new service work with PCI? Does the use of it already, do you inherit controls that help you with your PCI audit?
Absolutely. So this service falls into what we call at AWS our shared responsibility model. So in terms of PCI, we've built this service with PCI rules in mind. There are actually, people tend to use PCI, but there are multiple PCI standards and rules. But we have implemented the most common ones, PCI DSS, of course, which is the one that most people are familiar with, but also PCI PIN. You can see we're dealing with pins here. PCI P2PE, which covers card data and things like card data, like the 16 digits and securing that. Also PCI 3DS, 3DS is the additional authentication sometimes you do online, where you have to prove. Sometimes you get an SMS pop up in your app, things like that as well. So we've built this service to all those rules, and what you can do is, as a customer, you can take advantage of our shared responsibility model. So we've taken care of a lot of the compliance rules, especially that in regards to this, and you're able to take that and use that as part of your compliance. That won't get you 100%. You still need to do your PCI audit because there are things outside your application itself. But what we've done is we've taken care of a lot of the work. Also, we've built a service itself to be to follow a lot of these rules, to kind of enforce best practices when we can. So that is intended to keep you on the straight and narrow, as the saying would go, so that you don't run into any problem. For instance, I mentioned before, you can't use one key. One of the PCI audit things is, are you using one key for every single thing?
Right.
Which you can't do. The service actually out of the box enforces that you can't use one key for every single possible purpose. So that's just an example of how we just make it easier for customers to maintain their compliance.
Yeah, I think devs, like, speaking as a dev, and only having gone through like one compliance or two in my entire career, I think, it's this looming thing that you don't really know what it means, and you just know that if you don't get it, like, they're going to shut down your company. So you have to go out and get this compliance because you do payments, right, as a company or something. The first one that I went through, it's a checklist basically, and you have to prove out, like, okay, in my code, right, this is how I'm attaining this thing that you were requiring me to attain. And, like, this is where something like this can help you achieve that control, right? Help you check that box.
Absolutely. And what we do is we say, for those ones that we're either partially or fully responsible for, we share, this is essentially the answer. This is how we're maintaining that compliance for you, or this is how you can use our system to maintain that compliance.
Yeah. It doesn't get you the compliance. It helps you to check the boxes on the compliance.
Yes. Absolutely. And things like, and we expose things like audit logs through like CloudTrail and other AWS services. So these are some of the rules as well that are just built into the service.
Yeah, logging is a very huge part of PCI compliance and retention, et cetera. So yeah, that's great information.
Yeah.
Cool.
So Mark, if people are interested and want to try this out, is there a blog post or can someone run your demo that you're just working on, or what do you have?
Yeah, so we have I think somebody may have already shared it in the chat, but we have a workshop that we created. It goes through, it initially uses the CLI, at least this version of it, but it essentially goes through this very similar flow. So we think that's a great place to start. We think you can probably get started in probably 20 minutes, which is a huge, that just says a little bit about the benefit of this service, that we were talking about specialized hardware before that you would have in data centers with cameras and, floors that you can't access through. In comparison, this service, you can get up and running in essentially like 20 minutes and get a working, realistic, demo going. So we think that's a great place to start. We have our user guide as well. We're going to be publishing sample code in the coming weeks, and we'll definitely look to probably share this demo as well. So they can use it on their own.
Yeah, I was going to say this needs to go up, Mark. This is awesome. The toy store.
Yeah, I see Zach in the comments. He linked to the blog post has that ULD URL. That one works right, but I think there might be a problem with the demo that ends in ARQ. That takes me to a sign-on. I don't know if that goes to workshops or where that goes to, but if someone could check that link.
Okay.
Just to make sure for our viewers, because it looks like someone said it didn't work. I was just checking it.
For sure. Mark, clearly I could talk about this all day. I am fascinated by this world, but unfortunately we do have a time limit here at the show. Yeah, they remind me of it all the time, but I just ignore it most of the time. Anyway, any parting word?
Keep the mic off on you.
They try, but like I have full admin in our.
Yeah, he's actually running the show right now, so that's a little scary.
Yep, I could take this out till till midnight if I
Free
want.
bird.
Yeah, that's right. Just kidding. Only joking, of course. Anything you want to leave the audience, Mark, before we got to run?
Yeah, I mean, I would just say that definitely check it out. We think not everyone needs payment cryptography, but those people that do need it, this is a great option to consider. Really helps make it easier to use this type of service, maintain your compliance. It's an elastic service, which we didn't really talk about too much as well. You don't need to worry about, similar to Lambdas, which you guys were talking about earlier, or Fargate, things like that. This is a fully elastic service. You just start using it, and it scales essentially automatically to the capacity that you need. So no need to, reserve instances or purchase hardware or do high availability. We take care of all that stuff for customers. So we think it's a great option. The pricing is based on that as well. So if you don't have high volumes, the cost to use it is very low. And definitely try it out. I think hopefully we got that link working for the workshop. But just try it out and check out the user guide. We think it's very easy to use. And we're excited for people to start using the service.
Yeah, Mark, to add to your point, it seems that because handling payment information is sort of complex and you have to go through the audits and everything, a lot of companies will offload that process to like a company that specifically does that. It sounds like this service might help companies make it easier to say, we really wanted to handle the payments ourselves. This service makes that easier. Whereas maybe before this, there was all this cryptography involved. So I think that might help. Does that sound right?
Yeah, no, absolutely. This should definitely make it easier for people to maintain that compliance. That you don't need to go buy, $1 million of hardware. You don't need to have, the racks with the cameras and
right.
3 kinds of locks on them and so on. So
yeah,
definitely it opens up the opportunity, as well as also companies that are looking at regional expansion, things like that, where maybe you could justify it in your home market, but as you look regionally, it's hard to make the economics work, or even to start a new company.
Well, we talked about the 5 to 7 seconds, so I think that plays a role too.
Yeah,
absolutely. Yeah. And this is a service that we intend to deploy sort of locally in all the major AWS regions as well, so that customers do get that very low latency that they need for this kind of application.
Cool. Awesome, Mark. Well, thanks for joining us. We hope to see you again on the show sometime.
Yeah, absolutely. Thanks for having me, guys.
Thanks, Mark.
See ya.